The ones on web submissions are final mark unless you've copied from someone. Except for assignment 2, if you didn't pass test, was it fourth one, right, which I haven't looked through yet. Typically, your marks may stay the same, but potentially go down a little bit. But otherwise, yeah, they're not going to change unless you've done something silly. Okay. So there are two different systems. One, if web submission doesn't automatically get, or Canvas can't pull the marks from web submission. But if you can't see your marks on web submission, let me know. So there is a way to manually do this, but you know I can fit around and do it. Do you guys want me to try and import the marks into Canvas? Majority of hands. Oh, damn it. All right, so yeah, I'll go and have a look. I guess you get to see kind of an overall total, right? So yeah. Cool. So let's get started. So if you can't see your marks on web submission, let me know. But that's a problem. Okay. So where we stopped off last time was talking about distance vector routing. Just to quick recap. So we talked about link state and distance vector. Do you remember the problem with link state routing algorithms? What you run into, what we ran into, or at least what I've shown you? When you run link state algorithm, what problems can happen? Oscillations, right? Okay, cool. That's really good. And could we stop oscillations from happening? What was the problem with oscillations? Oscillations happen because of
using a bad cost function.
Bad cost function. Pretty good. Cool. So what was the cost function we used in the example? We used. Sorry. No, amount of traffic, right? So we used the amount of traffic. Turned out to be a bad idea, and to overcome that, the simple solution was to use number of hops, right? The hop count would be a better metric. So we talked about distance vector, and distance vector is centralized or decentralized type of algorithm? Decentralized, right? So the main reason is because you only tell your neighbors, right, about what you know, and it's neighbor's job to propagate that information throughout. So in terms of link state routing algorithm, we went through this example. Sorry, distance vector routing algorithm, we went through this example, and where we stopped off was, I think, to say that essentially there's no update being sent from Y because Y's routing table doesn't change as a result of the messages it gets. And if just as an exercise, we could see what happens here, just to recollect your memory maybe, right? So let's assume that at X we got a message from Z, right? So in this case, we look at the Z column, right? So this is going to get updated because now we're going to find out some new information about Z's shortest path, right? So Y is just not going to change. So and the first one is this is not going to change because this is my direct link, right? It's 7. So does Z have some new information about how to get to destination Y? So it can get to destination Y with the cost of 1, right? Plus what's my cost of getting to Z? So I'm at X. X Z is 7, right? So 7 plus 1 is 8. Okay, so that means from this point onwards, the distance vector table hasn't changed, and the shortest path's information hasn't changed. So the routing table doesn't change. So do we send any messages forwards from this node? No, we don't send any messages. Why? Because there's no change in the routing table, because the shortest paths are still what we know, right? These two, okay, they haven't changed, right? So no messages are sent, okay? Just a quick example. Let's do one more. So let's do the last one. Let's see, we are here. So we're getting a message from X. So we're going to be looking at updating the information in this column here. And so Y, that's not going to change. So because we don't get anything from Y, 3, Y to Y doesn't change. And we have X to X cost. That's not going to change. That's a direct link, right? So what information does X have about the shortest path to Y? So it says its cost is 2, right? And what's my cost of getting to X? So it's a 7, right? So 7 plus 2, it's a 9, right? Okay. So in this case, we can see that the shortest path is still 3 and 1. So essentially, this node will no longer send any updates, right? Because his routing table is not going to change, right? See, the shortest path is still the same, right? Okay, so it'll now stop sending any updates. So eventually, the algorithms will converge, right? Okay, and it'll stop running. Is that good? Okay. So, you know, how you doing? It's not all, it's not always good, but here's the case when it is good. So with linked state routing algorithms, distance vector routing algorithms, good news travels fast, right? So here's a quick example to illustrate why that is the case. So it's the same network as before. So sorry, this is X here. This is Z, and this is your Y, right? So let's assume that this is the initial distance vector table, and at Y we have cost of going to X. This is the direct link, which is 4, and cost of going to X via Z is a 6, because you can see a loop here, right? Why is that? Because if you go to Z's routing table here, you have direct link is 50, but it says, oh, I can get to X via Y because I go here 1, and then Y thinks, oh, Z has a cost of 5, so that's why it's a 6 here, right? So there's a routing loop here, right? Okay. So when Z wants to go to X, it will send to Y, and Y will send to Z, right? And then Y will eventually go here, okay? Sorry, Z will send to Y, Y will send to X, and Y will send directly there, right? But look what happens when, let's say, this link cost reduces over time, right? So essentially, did I say this correctly? So in terms of Z, if it wants to go to X, it sends to Y, right? Okay, and if you're at Y, obviously you take the direct link, right? That's where we're at. So let's say this link cost reduces over time, and so what that means is, so there's a link state update here. This cost has gone to Y, so that means Y's routing table will change because it'll now have a new cost, right, of getting to X. So that means it will now send its neighbor, tell its neighbor, and send a message that I have a new cost of getting to X, which is 1. And in this case, Z will look at Y's column, and then we'll go, right, so Y can get to X with a cost of 1, I can get to Y with a cost of 1, so the total cost is 2, right? So this will result in Z changing its routing table because it has a new cost, right, of getting to Y, so it'll update the cost of getting to, it'll update its cost of getting to X, sorry, and then it will send a message to its neighbors. So let's assume that message arrives at Y, and then Y will go, right, okay, so if I look at Z, it's over here, and now I can get, if I want to get to X, the cost is, I go here, and Z says I have a cost of 2, so 1 plus 2 is 3, right? So it updates its cost. But you can see in this case there's no loop, right? Why? Because this link cost is still lower than what Z is reporting, right? Yeah. In all these cases, this cost is lower than what Z is reporting, right? So Y will still continue to route this way. So if you have good news, that is the link cost reduces, then generally the routing algorithm propagates that cost, and tables will converge fast, right? The opposite example is if you have bad news, right, which is, in this case, the same network as before, Y, X, and Z. So, but now the link cost here is going up, right? So we start off in the same place as before, right? So 4, 6, 55, but there's a link update here, okay? So Y's cost of going to X is now 60 because the link has gone up. But so Y will recompute its routing table and start routing its traffic via Z, right? Okay, because this cost went up. So it will go, right? I'm going to send all my traffic to X, to Z, because Z is telling me that it can get to X with a cost of 6, right? So Y has no idea that Z is actually routing via Y, okay? So if you look at Z's routing table, it's actually saying, oh, if I want to get to X, right, I have a cost to get to X via Y with a cost of 5, right? So Y is routing to Z to get to X, and Z is routing back to Y, right? So we have this loop, okay? Right? So because this went up, right? Bad news. Fortunately, this will eventually resolve itself, but it's going to take some time, and hence the name count to infinity problem, right? So what will happen is basically they're going to continue to send messages back and forth between each other, and eventually eventually Z will start routing traffic this way, right? Okay. How does it happen? So if you look at the next update, so now Y goes, hey, I have a lower cost to X, cost of 6, and tells Z. Z goes, oh, wait a minute. So Y's just cost went up. So that means my cost of going to X is going to be the cost of getting to Y plus Y's cost of getting to Z, which is 6, right? So this is 1 plus 6 here. And then Z goes, oh, I have to now update my routing table. So it's going to send a message out to its neighbors. And then because Y is routing to X via Z, it'll go, oh, now Z's cost of going to X has increased, right? So it's going to increase its cost as well. So this dance is going to continue back and forth, right? Yeah.
Would it be quicker overall to just redo all the routing from scratch?
No, sure, it will. But the trouble is the way the algorithm is decentralized, right? So it doesn't. So the point here is that it's Y is not aware that Z is actually routing. Its shortest path is Y itself, right? Okay, because there's, unlike in Dijkstra, where every node has full visibility over the whole network. In this case, you don't. Right? So that's why this problem occurs. So eventually, this will stop when? What needs to happen? Yeah, what needs to happen for Z? How long will this go on for? 6, 7, 8, 9, 10, 11, 50, yeah, until Y's cost gets to 51 and Z cost get to, for X gets to 50, right? Eventually it'll find this as the best path, right? So this is going to keep increasing, but eventually it needs to go higher than 50, right? It needs to get to 51, it'll go, right, route directly. Okay, so this number just needs to keep going up, right, until it's like 51, and then Z will eventually start routing directly, right, instead of sending to Y, and Y will eventually get a cost of 51, right? Okay, because Z will report back and say, oh, my cost of going to X is now 50, and Y will go, oh, okay, now my cost is going to be 50 plus 1, right? Is that clear? Any questions? So yeah, it's a cool name, I guess, count to infinity. So if this number was very large, it could go on for a long time, right? And until then, you're like kind of stuck in a loop, right? Routing loop. So you can get routing loops as a result of this type of scenario where you have bad news that travels slow. And that's unfortunate side effects of distance vector routing. So how do we stop this stuff? There are some remedies. And one of them is called poison reverse. So you guys are using Cisco routers for your prac. So they, I think they use what's called split horizon, which is not the same as poison reverse. So you might want to read up on that one. They're very similar in concept, but subtle difficulties. So let's look at a simple way of preventing it. This. So what we need to do is that here, so this is what we had before, right, at Y, But now you'll notice that when you in Poisson reverse, the idea is that because y is now you'll see here that y's cost of going to x, y, z is infinity. Why is that? Because before it was 6, right? It's infinity now. Why is that? Because z, who knows that it's routing to x via y, advertises to y its cost of getting to x as infinity, right? Because it's routing via y, right? So instead of z saying, hey, my cost of going to x is 5, it says that my cost of going to x is infinity because I'm routing through you, and I don't want you to route to x via me, right? Because I'm already using you to get to x, right? So here, actually, z is advertising a cost of infinity, right? Okay. So instead of the 5, to prevent y from routing via z, right? Because z is already routing via y, right? So you're poisoning this reverse path, right? So if you do this, so let's assume that you're using Poisson reverse, so routing loops are not allowed, so you start from this point here. And then at the next stage, let's assume the same thing happened. So this is our event, right? That happens. Boom, okay? So the event happens here, and this cost goes up to 60, and automatically y will go, oh, I can't go via z, it's a cost of infinity, so it'll use the direct link, right? And then its routing table is going to change because its cost of going to x has changed, so it's going to send a message to z, its neighbors, and say, hey, my cost of going to x is now 60. So z will go look at, sorry, where am I? Here. So z will look at the y column and will go, right, so y's cost of going to x is 60, and my cost of going to y is 1, so my total cost is 60 plus 1, right? It'll update its routing table, okay? And then immediately what happens is it used to route via y, right? Now it's going to use the direct link, this one, right? Okay? So as a result of this, z's routing table is going to change, right? Okay, so it needs to send a message to let all its neighbors know, hey, I have a new cost of getting to x, and that's 50, right? So z will go, because now we're no longer routing via y, so z here doesn't have to advertise the cost of infinity, right? Okay, I don't need, yeah. So it just advertises the cost, its cost. So then y will update its routing table correctly, right? Is that clear? Confused? A little bit? So essentially, z tells y its distance to x is infinity, y, so that to stop y from going through z that way, right? The way it does that by realizing that, oh, my shortest path is through y, so therefore I'm going to tell y my cost of getting to x is infinity, right? But in this case, z's path to get to x is its direct link, right? This is a direct link. So in this case, it says my shortest path to get to x is 50, right? So it looks down this column here, and it goes, oh, so you have a new cost. It went from infinity to 50, right? And then my cost of getting to you is 1, so you have 50 plus 1 here. Right. Okay? But before you were advertising an infinity, right? Because z was routing via y. Poisson reverse, is it always going to work? Does it solve all problems? Yeah, probably not. That's a good guess. Yeah, no, it turns out it's only really good at this kind of simple network with 2 hops or 3 nodes, right? If you increase it, yeah, it doesn't work so well. So if you have, maybe you can Google or you can try to find something. But if you had a network like A, B, C, something like that. 4 nodes, it's not going to work anymore, right? So maybe first you're routing via this way, so you advertise to C, your shortest cost to get to D is via A, right? And then maybe this link goes down, right? And C will now start routing to D via B, right? And B will go to A will go to C, and hit a loop again, right? So it's very simple to come up with a network where, yeah, it doesn't really work. But it works for small networks. So it's a difficult problem to solve. And Cisco uses a choice between poison rivers. I think you can set them up as, split horizon. So there's a slight difference. I'll let you guys find that out, okay? All right, so this is the important part. You may have seen some exam questions that may have asked you to think deeply. So in terms of these 2 routing algorithms, which really dominates all routing algorithms on the internet, right? Link state and distance vector, that's what they're all, some variant of this stuff, right, out there. So how many messages does link state need to send? So you know that each node needs to send the cost of each link, right? In link state, each node needs to send the cost of its links, right? You need to tell everyone. If I have 5 links, I need to tell all the other nodes what those link costs are. So that means you're going to have, if you have n nodes and e links, so links means, so this is a link, right? Okay, that means if I have n nodes and e links, I need to send ne messages, right? So that the entire network knows the cost of all the links, because each node needs a view of the full topology, right, of the network to run Dijkstra, otherwise you can't. Okay, distance vector, you don't really do that because all you advertise is to your neighbors, right? Okay, so exchange between neighbors only, but the bad news is that conversion times can vary. Now you've seen an example of that. So you had the good news. The good news, bad news example, right? Good news travel fast, bad news travel slowly. Okay, so the time for the network to converge, that means for all the nodes to get a full idea of the cost of traversing various paths is going to take. It depends, really, right? Okay. Speed of convergence. So we looked at the complexity of Dijkstra. I said the worst case. This is worst case, if you remember. Right? Is order n squared. Can be better. So you should have an understanding of why that is the case. And one of the problems is leads to oscillations. You should have some understanding of why and how, right? Okay. Distance vector. Convergence times varies, as we mentioned up here. Same reasons, right? And you can have routing loops, again, right? An example is the count to infinity problem, right? Okay, where you have bad news. In terms of robustness, what happens if a router malfunctions? That is, one of the routers goes down, or maybe you advertise an incorrect link. So if you look at link state, basically what will happen is, if you advertise an incorrect link cost, right? That is a disaster, right? Why? Just randomly picking that up. I mean, if you advertise this cost is actually 4, but it's 60, advertise it as 60, and this information in a large network can propagate everywhere, right? Okay, and that's bad, right? Because everybody is going to come up with very bad routing tables or wrong routes, right? As a result of that. But if the same thing happens with distance vector, that's not so bad. Sorry, if the same thing happens with, link state, apologize. If the same thing happens with link state, each node has a full view of the topology, and each node independently calculates the routing tables, right? Okay, so in that case, if one node was to advertise a bad cost, it's not so bad, right? Because each node will compute parts on its own, right? Whereas with distance vector, because you have this whispering business that goes from node to node to node, that information will propagate everywhere, right? And it's very difficult to rectify that, as you saw, right? Bad news travels slowly. So time to convergence can vary, and then so distance vector routing algorithms are more affected by these kinds of incorrect link costs and router malfunctions, right? Okay. Here's the part we slightly looked at, then we kind of skipped a little bit. So I told you that the routers that you guys are working with have both the control plane and the data plane implemented on the router itself, right? They're both sitting on the same device, right? But what I said was that kind of the world is moving towards where we're going to take the control plane and separate the data plane and control plane, right? And put the control plane somewhere else. What goes in the control plane? What happens in the control plane? Do anyone remember? Does the control plane have the routing algorithms, or does it have the forwarding tables? Perfect. So it has the routing algorithms, right? So routing algorithms churns numbers, looks at stuff, and spits out the forwarding table, which the routers use to forward packets, right? So going back to that, so traditionally, control plane is implemented on the devices, right? So like the ones that you guys are looking at. So, and each router has both the control plane and the data plane. Control plane calculates the routing algorithm, so you might see things like IP, RIP, RIP, OSPF, Open Shortest Path First, BGP, etc., right? And all of these are variants of link state and distance vector routing algorithms, okay? So you pretty much know everything, right? Variations of them. And I also mentioned how increasingly networks are becoming kind of a place for different types of devices, from firewalling to switches to routers to, you know, deep packet inspection devices, blah blah blah. There are intrusion detection systems, etc. Right. So the motivation that I mentioned was to separate the control plane, was to kind of take away all this functionality out, keep it, and then do it somewhere else, and control all these devices in a single systematic kind of way, right? So that's kind of why people started looking at software-defined networks, where the behavior of the network can be systematically controlled just using software, right? And so people have been doing research for a while in this area. People are still doing research for a while in this area to kind of realize the vision, or if you like, and maybe the thing that hasn't happened is performance, right? Has been why the uptake has been slow. But really the motivation I want to illustrate by using a couple of examples, okay? So motivation, why might you want to take the control plane out of the routers, right? Okay. Traditionally, that's become a pain point, is what's called traffic engineering. So if you're an internet service provider, and then you're responsible for managing large networks, you get traffic from all sorts of people, your job is to route and, you know, achieve certain performance metrics, you get paid for that. And one thing everybody wants to do is what's called traffic engineering, right? Okay, what does that mean? Well, here's an example. So what if a network operator wants U to Z, so here's U, here's Z, right? Traffic flow via U, V, W, so we need to go this way, okay? Right? But the shortest path algorithm says, you know, go this way. Why? I don't know. Maybe there's a security reason why we want to do that. Right? Maybe it's ASIO and they don't want the traffic to go via these nodes and they must travel this path, right? Okay, so I want to be able to treat this traffic flow going to the same destination differently, right? So if you use any of our routing algorithms, is that possible? Can we do that?
Yeah, you could.
How?
If you basically set links to
Yeah.
infinity.
That's right. So you have to engineer traffic cost, right? You have to engineer cost metrics such that fudge numbers so that it, you know, this becomes the shortest path. But I can't differentiate between two flows, right? What if this is organization A and what if this is organization B? Right? Routing decisions are not based on the source IP address, right? They're based on destination address. I don't care where traffic comes from, right? I only care about where it's going. So there's no real easy way to solve this problem, right? Okay. So the solution is ugly, I guess. So you need to define link weights. So traffic routing algorithms computes routes accordingly, and this is okay for one. But then if you want to differentiate two, you're kind of stuffed, which is, I guess, my next example. So you want to split traffic, right? Maybe load balancing. Load balancing is a classic example, right? You always have to do this, right? You have one link that's chock-a-blocks, but it somehow is the shortest path. You can't use traffic as a metric. You get oscillations. So, what do you do, right? So you want to be able to divert traffic, or this provider is, this customer is paying you more money, so I want to provide a high throughput, low latency link. How do I do that, right? Okay, so, and that's not easy. You can't really do it using routing algorithms. There's no solution for this using routing algorithms, right? Because routing is always based on destination address, not source address, right? Okay. So here's another kind of security kind of example. If W wants to route blue and red traffic differently, again, so I got two traffic flows from two different A and B organizations, right? Shortest path says, boom, shortest or best, right? But for some particular reason, I want to send it this way. Security, traffic engineering, whatever. There's no elegant solution for this based on a link state or distance vector routing algorithms, right? That always gives you the lowest cost metric path, right? There's other stuff, like you might want to do, so you may have firewalls that looks at, dropping telnet traffic. So you may have tried to telnet to some like www sites and they may not let you do that, right? So they won't let you connect because there's a firewall that's blocking it. Or maybe you find that there's a denial of service attack and this traffic this is a DOS attack, right? Denial of service, that is somebody's creating some fake request to keep things busy, right? I want to be able to drop these packets because I know that it's happening, right? Dynamically, right? Routing algorithms won't let you do that. They'll just route those packets, right? Okay, so there's lots of reasons why you want to have some control over the control plane, how it behaves, right? And be able to consistently manage a large number of devices, right? So you've seen this already from me. Just to recap, right? So what you have is essentially, in terms of software-defined networks, what we have are what I call, I have an example next, flow tables. Okay, so that's what routers have, and then the flow tables are computed using a controller, right? Which has, and then the controller may make decisions based on maybe load balancing, maybe security reasons, maybe shortest path, whatever, right? So it may have multiple reasons how it decides to make these flow tables, okay? And then it propagates those flow tables to the data plane of the routers, right? So the controller can exercise whatever it thinks is best, right? And makes its decision not just based on the shortest path, could be where it's coming from, whatever, some attack that's happening, load balancing, whatever the need is, right? Okay, and then compute what the flow tables ought to look like to manage the situation, right? So that's what happens in software-defined network. We don't want to go in too deep, but just to give you an idea of a flow table and how that's different to a routing table, right? So this is not the same as a routing table. So we've looked at routing table. Routing table has destination field and some cost, and an outgoing link for that destination, right? Okay, destination A, what's my link? Destination B, what's my link? That's it. So a flow table is slightly different. Flow table has headers, has counters, and actions. So headers are really cool because now headers don't just span IP. These headers can span any of the protocol layers, right? It could be MAC addresses, it could be port numbers, it could be IP addresses, it could be source IP addresses, it could be destination IP addresses, right? It could be whatever, right? So it can span multiple protocols, okay? And then the actions just tell you if you have a match, right? If you have a match, then what action should I take? If my header matches this, what action should I take, right? So this is basically a forwarding action, right? Well, you can have more than forwarding actions. You can even drop packets, do whatever, or send it for deep inspection, right? So it's very flexible. So instead of routing tables, now we have flow tables. And flow tables can match not just across the IP address, but a whole bunch of headers across a whole bunch of protocols, okay? So here's an example, right, of so OpenFlow protocol is an open source. I guess you can go and search and download this stuff and play with it. Yeah, OpenFlow. In the OpenFlow protocol, I'm just going to point out an example of a flow table and what that looks like. Okay, so remember there's 3 entries, right? The header, stats. Oh, didn't mention stats. Sorry. So that's counters. So counters is like, so basically this is your statistics, right? So if this is a match for, let's say, UDP type traffic, this will keep track of, you know, how many UDP packets you've seen, for example, right? Or if this is a header for, you know, data going to destination A, this will count the number of packets you've seen going to A, for example, right? So that keeps statistics, okay? Right, yeah. So we have a rule, that's the headers you want to match across. So rules are the headers you want to match across. Counters are here, keeping track of stats, right? And then action is here, right? What do you do if you get a match for this rule? Okay? Yeah. So in this example, some of the actions here. So forward the packet to. So forward the packet to ports. This is traditionally what routers have been doing, forwarding packets. But it's a whole bunch of other cool stuff. You can encapsulate and forward to a controller. So you can go, hey, this packet looks suspicious, so I'm going to send it for deep inspection to a controller, right? Okay. You can drop packets. You can go, hey, denial of service attack, right? Maybe drop these packets, or do some firewalling, right? Okay, implement some firewall rules, right? Send to normal processing pipeline. So this, you know, no deep inspection, just send it straight through, right? You can even modify fields, right, if you needed to. Okay, maybe you want to manipulate those packets path it takes. Maybe you can modify some of the fields. It could be quality of service field, right? So there's a whole bunch of different actions that you can take now, whereas before all you did was just forward packets, right? That's all you did, routers do. But now you can do all this cool stuff. So in terms of rules, right? So here's a bunch of examples that you can match across. You can match across ports. You can match across virtual local area network IDs, VLANs, right? So you can set up virtual. We'll briefly look at that later. So MAC addresses, we haven't looked at link layer yet, but MAC source and destination addresses, Ethernet type, IP source destination addresses, port numbers, TCP source port destination port. You can match across a whole bunch of stuff that you were not able to do before, right? So here's a few examples of flow table, right? So this flow table entry basically is looking at a match across IP, destination IP address, blah, and the action is that IP datagrams destined for IP address 51.6.0.8 should be forwarded to router port output port 6. So this is a traditional, you know, like a forwarding table entry, right? If you see something going to blah, send it to this link, right? But here's a firewall entry. Do not forward or block all datagrams destined to TCP port 22. So you have an entry in your flow table that is now matching across anything with any traffic that has destination port 22 and dropping it and not forwarding them anymore, right? So the router is actually doing that now by using the flow table, right? Okay. Here's another one. So do not forward or block all datagrams by host. So here you're looking at destination port. Now you're looking at where it's coming from. Don't trust this guy. For security reasons, do not forward any traffic from organization A, right? So now you're blocking based on the source address. This was not possible before, right? All routing decisions are based on destination IP address, right? Okay. Are you convinced the power of SDN? No. Everybody say no. Sorry. Yes. Right. So the last thing I want to talk about is IPv6, which is something I postponed earlier, right? Because I wanted to cover the routing algorithm. Do you have any questions so far? Anything burning other than assignment marks on Canvas? You just want to keep me busy, right? It's okay. I get it. Any questions so far with network? You good? Okay. So, a long time ago, people wanted to decide how many bits to use for an internet address. And they decided 32-bit was enough. Well, clearly, when the internet started, there was like 2 or 3 machines, right? So that was, you know, overwhelming number of addresses, right? But as time went on, came 1980s and 1990s, and people predicted all the IP addresses are going to run out by like something like 2008, 9, 10. And then because, nobody expected the boom provided by the www, right, World Wide Web, and everybody got on and so many machines got added, and so the purpose of the internet or the way it was evolving changed rapidly, right? So one solution was that to amalgamate IP addresses I told you about. Remember class full addressing, right? You could get 2 class A addresses or 2 class C addresses, right, to a single organization. But if you start amalgamating this, then what happens to routing tables? The routing tables are going to need more entries to be able to route, right? So you can have growth in routing tables. That means routers are going to run slow, right? So luckily, fortunately, CIDR addressing came along, right? Which is said, well, we got to, dump this rigid boundary, and then let's use classless addressing, right? So we looked at classless addressing where we define a network, right, and a host portion flexibly using a subnet mask, right? The mask defines a boundary between the network and host bus. They were not split along the 8, 16, 24 boundaries in the classful addressing, right? So this classless addressing took care of the problem, and the internet didn't die around 2008 and continued to evolve, right? And then also we also use network address translators. So what that means is that Adelaide University advertises maybe 129, 127 dot something, something, something to the rest of the world, but internally, right, I could have a large number of private IP addresses, right? But when those IP addresses need to go out of Adelaide University network, I translate them to a 129.127. Blah, right? So the rest of the world only sees one IP address, but internally I translate them back to all the private IP addresses, right? So these kinds of technologies kept the internet going, although IP addresses were running out. So example, I told you that all class B addresses are gone, right? So this thing about internet needing a new internet protocol, or at least needing a larger address space, started way back in the 90s, right? So it's been going since 90s, 28 years. And we're still evolving along this journey and haven't quite completed that journey. And we are predominantly still using IPv4 addresses, and the internet hasn't died, right? We're massaging the situation going forwards. So the key question was, what do you do, right? How many bits are enough? Do you go to 32 to 48, 50, 1024? What's the number going to be, right? Should we go back and rejig IPv4, right? Change a bit of things. So the decision was decided that the best thing to do was to create a new protocol, new version called IPv6. So there has been a whole bunch of suggestions and ideas that came along. Eventually we'll go to a standardizing committee meeting, right? IETF, and they'll discuss stuff. People, involved parties, including you, can get together and provide comments, right, that are proposed, blah, blah, blah. And time goes by, and eventually IPv6 was decided. And in terms of agreeing on what is enough, so the idea was that, well, maybe 128 bits might be the right number. Maybe 256 is too much. So the idea was that if you had an IP address that was 128 bits long, you could potentially have an IP address for every molecule like on the planet, and then surely that should be enough, right? Who knows? Because nowadays we are giving IP addresses to like cups and shoes and chairs and all that, rulers and all that kind of stuff. But if you look at it in terms of density, so I think there's a number like 1,000 addresses per square meter is roughly within efficient addressing. So if you're going to have more than 1,000 devices in a square meter, that's pretty dense. That might again be possible. I could potentially have about 20 IP addresses on myself. Wearables, who knows, right? iPhones, glasses, right? Smart shoes, smart pants. So yeah, maybe we'll run out. What about intergalactic travel? Maybe we go to Mars and colonize Mars and we go, crap, population doubles and we go, that's not enough. So we don't know, but right now it's going to be 128 bits, right? That's the way it is, and that's what was decided to be able to support future IP protocol. Now, because 128 is really long, instead of using the dotted decimal notation, which you saw earlier, everything's written in hexadecimal, so base 16 numbers, right? And these addresses are really long, so the way you write it is using this colon. So you have 1, 2, 3, 4 hex digits, colon, and blah, blah, blah. But there's a little bit of shorthand here. If you have a large bunch of zeros, and you can compress that without ambiguity, that means if it's going to make the address ambiguous, don't compress it, right? In this case, These are the only zeros, so it's not ambiguous to compress it by putting 2 colons there, right? So again here, right? Because there's so much writing, and here, right? As long as it doesn't make the address ambiguous, you can compress it. So the difference being now we use 128 bits, we express it using hexadecimals, and we have a tiny shorthand way of compressing these addresses into smaller addresses, right? So in terms of IPv6 routing, these addresses are hierarchical. They have something really cool here. So unicast. Unicast is basically an interface as a unique IP address. And if you send to a single IP address, that's unicast, right? So we talked about broadcast. So remember, in a network, if you set all the host bits to 111, that's a broadcast address that goes to everyone, right? So you know about broadcast. So there's a couple of, we talked about multicast in IPv4, and a classic example I gave you was in terms of IPTV, where you have multiple subscribers and a single content provider, and then you have to send the same packet to multiple people. There's no point sending it same packet from the source to all the destinations, but you send it to a multicast address, and you join in as multicast subscribers, and multicasting routers can take care of splitting when required, right? That same piece of data. But the thing that's new is in IPv6 is basically anycast. So what that means is that, so let me give you a good example for that, is basically thinking about, so you guys download stuff, and do you get taken to select a mirror site? You know, pick the mirror in Japan, UK, Australia, whatever, yeah? Have you had to make that choice? You have? Good. So instead of doing that, you could use an anycast address, right? When you want to download, you send the download request to an anycast address, and anycast address will find maybe the closest device or one of many cluster of devices, right? Instead of going manually selecting the mirror site that you want to use, right? So there's this introduction of anycast, which identifies not a single interface, but a set or a group or a cluster of interfaces, or the nearest interface, right? So you can deal with that. So there's that flexibility. So this is new. And the other thing that's new in IPv6 is a long time ago when IPv4 was there, you got a device, you know, it's like a giant computer, you plug it in, you're not going to carry it around with you, right? There's no mobility. There were no mobile phones or iPads or iPods. But now in IPv6, you know, I have a device, I plug it in, I have an IP address. Maybe when I go to the US, I want to use the same IP address, right? I want IP number portability, right, across networks. So how do you support this kind of thing? So IP mobility. So it does have support for some of these cool things that people may want to do in the future. So other than that, in terms of the address space, it's hierarchical, right? Why do you want to make the address space hierarchical? Simple. Want to make routing simple, right? Okay? Because if you make these routing tables grow, it makes everything slow, right? More entries you got to search, the slower it becomes. So in terms of hierarchical nature, what you have is, so you have a subscriber prefix, area ID, so subscriber internet service provider. Area ID could be geographically location, and you have a subnet and interface ID, right? So subnet is like before network and host paths, right? Okay, so if you like, so this is your network and host paths, right? So it gives you an ISP and a geographical location. So if I see an address of this, then I know, so the top level domain routers just need to, okay, just send it that direction, right? And when they go there, oh, this looks like in Australia, right? Okay, let's send it to some router in Australia, right? So it makes routing simpler, okay? This is the part I want to look at in a little bit more detail, running slightly out of time. Right, so here's a IPv6 datagram, this packet side by side with an IPv4. So just as an exercise, what do you guys notice? What are the differences? What's still here? What's missing? No options, yes. So options, there's no options field, but options are there in a different way. Yep, you're right. Sorry?
Sorry, the options are now flow label, right?
Options are there, but I'll talk about it in a minute. But options are supported, but it's not in the header. Yeah. Somebody was saying about flow label, I heard, right? Flow label, so this is, where is it? So this is new, right? Yeah, thank God there